So today we are going to start talking about some applications of integration um, for business stuff. Um, well, not just for business stuff, but kind of just applications of integration in general. Um, the first one that we're going to talk about is finding the average value of a function. Um, and it's a pretty straightforward application of integration. Um, if we have some function and we know the area beneath that function, what we can do is we can take a rectangle with the same area as the function. And if that rectangle has the same area, then the height of the rectangle is going to actually give us the average value for the function. Um, so basically we find area beneath the function. So if this is f of x and this is a and this is b, then the area beneath that function is just the integral from a to b of f of x dx. Recall that this is the definite integral from a to b of f of x, and it gives us the area between, or the signed area, between the x-axis and the curve. And if we take a rectangle, so the area of our rectangle is A is equal to h times w, where the height of the rectangle is the average value of the function, and the width of the rectangle is, well, the same as the width of our function. It's the same as the interval that we're looking for. So width of interval. And this area is the same thing as our integral. So the integral from a to b of f of x dx is equal to the average value times the width of the interval. But the width of the interval is just b minus a. B is over here, a is over here. This distance is just the difference between the two. So we get our average value formula, which is probably best stated. Of course, I closed my notes. So if f of x is a continuous function on the interval AB, then the average value of f on between A and B is f average is equal to 1 over b minus a times the integral from a to b of f of x dx. So that is our average value formula. Okay, an average value can actually be, it can be applied to marginal costs, marginal profit type stuff. Let's do an application without context first, just finding an average value, and then we'll do one with a little bit of first. So let's find the average value of f of x equals let's do 4x squared minus 7x plus 12 on the interval -2 to 5. So to find this average value, we're just going to apply the average value formula. So f average is equal to the integral, or 1 over 5 minus -2 times the integral from -2 to 5 of 4x squared minus 7x plus 12x. So that's 1/7. And we can integrate here. The integral of 4x squared is 4x cubed over 3 minus 7x squared over 2 plus 12x. And this is evaluated between x equals -2 and 5. So remember that to evaluate definite integrals, we're using the fundamental theorem of calculus, right? So recall the integral from a to b of f of x dx is equal to big F of x from x equals a to x equals b. And this notation here, this bar back here, that just stands for big F of b minus big F of a. We're evaluating it at the upper bound and evaluating it at the lower bound and then subtracting the two results. So let's go ahead and plug in some values. That's 1/7 of 4 times 5 cubed over 3 minus 7 times 5 squared over 2 plus 12 times 5 minus 4 times -2 cubed over 3 minus 7 times -2 squared over 2 plus 12 times -2 . And we should go ahead and evaluate this. You can plug this into a calculator right now if you want. I would probably plug it in smaller pieces. So 5 cubed is 125. So 4 times that is 600. Sorry, 500. 5 squared is 35. 7 times 35 is 245. And it's not 35, it's 25. 7 times that is 175. Plus 60. Minus, so -2 cubed is 8. 8 times 4 is 32. So this is actually going to be plus 32 over 3. 7 times -2 squared is 28 over 2, which is 14. And this negative and this negative will cancel. So we get plus 14. And then plus 12 times negative 2 is going to be plus 24. This, I figure, we might as well just plug this into a calculator. Like I said, we could have done it earlier. 1/7 of 500 over 3 minus 175 over 2 plus 60 plus 32 over 3 plus 14 plus 24 is going to be about 26.83. Repeating. So
wouldn't that have been negative 24?
Yeah, I was just gonna say this.
So it is a negative 24, but we're subtracting the whole thing, right?
Oh, gotcha.
Okay.
Before the parentheses.
So the negative sign, I distributed that as well. That's why this is a positive 32, because it was a negative 32 on the inside, or positive 32 over 3. It was a negative 8, but then the negative sign on the outside made it positive, right? Same here. These two negative signs cancel. So,
Gotcha, thank you.
so the average value of f of x between x equals negative 2 and x equals 5 is 26.83. And we could look at a quick graph here if we wanted to, just to verify our math intuitively. 4x squared minus 7x plus 12 is what our graph looks like. And let's go ahead and throw a line in at y equals 26.8333. And let's go ahead and make our window between negative 2 and 5. And we'll go between 0 and, 30. There we go. And you guys can see the blue line is our average value, while the red line is our function there. That blue line represents the average value. So sometimes it's a little bit lower than the red line, sometimes it's a little bit higher than the red line, but on average, it's... So the areas beneath those two curves are the same, is what I should say. The area beneath the blue rectangle and the area beneath the red parabola will give you the same exact area. So suppose your marginal cost to produce a product is C of x equals 4 minus 0.2x squared. How much will it cost on average to produce the first 10 objects or products? So this is asking about an average cost. I've given you a marginal cost, which is the cost. It tells you how much is the cost to make the xth item, right? So if you have a marginal cost and you plug 5 into that, that'll tell you how much it costs to make the 5th item, right? But what I want to know is what's the average cost spread out over the first 10 products, right? So here we can use the average value formula. So the average cost will be the integral from, we're talking about the first 10 products, so that'll be from 0 to 10. We want our area to have a width of 10. Of 4 minus 0.2x quantity squared dx. So this integral,
quick
yeah,
question.
go ahead.
Why are we not using the 1 over b minus a in this situation?
Because I forgot to write it down.
Oh, okay.
Thank you. Good catch. The average cost is 1 over 10 minus 0. Thank you. So here, to evaluate this integral, we could do two different things. We could either multiply this out, or we could try a u substitution. Because u substitution is our newer method, I'm going to go ahead and do the u substitution. So in this situation, I want u to be equal to 4 minus 0.2x, which means that du over dx is going to be equal to negative 0.2. The derivative of u with respect to x, we take the derivative with respect to x on both sides, we get negative 0.2. Multiply both sides by dx, du is equal to negative 0.2 dx. And then we can divide both sides by negative 0.2, which is the same as multiplying by negative 5. So negative 5 du is equal to dx. So our average cost integral is equal to 1 over 10 times the integral from x equals 0 to x equals 10. So because I'm changing the variable of integration back here, I'm going to make sure that I remind myself that my bounds are x bounds, not y bounds, not u bounds. Okay, so I'm going to need to back substitute before I can plug in my bounds for this integral, and that's going to be u squared times negative 5 du. We can bring the negative 5 out front, so that's negative 5 over 10 is negative 1/2 times the integral from x equals 0 to x equals 10 of u squared du. And the integral of u squared is u cubed over 3. And we're going to evaluate that between x equals 0 and x equals 10. Once again, we don't want to evaluate this before we substitute back. So we're going to put our x back in here. We'll have negative 1/2 of 4 minus 0.2x cubed divided by 3. And now we're going to plug in our bounds. So that'll be negative 1/2 times, first we'll plug in 10, so that's 4 minus 0.2 times 10 over 3, top is cubed, minus 4 minus 0.2 times 0 cubed over 3. So this is negative 1/2. 0.2 times 10 is 2. So 4 minus 2 is 2. So that's 2 cubed over 3 minus 4 cubed over 3. That's negative 1/2 of 8 over 3 minus 64 over 3. Which is negative 1/2 of negative 56 over 3, which is also equal to positive 56 over 6. Which, if we want to write that as a decimal, is about 9.33. So the average cost per unit is 9.33. So essentially the idea here is that you're finding the total cost, which is taking the integral of marginal cost, and then you're dividing that by the amount of units that you had. But we're just viewing it from this more geometric lens, right? And using this average cost formula. Any questions about finding average values? This formula here. Either of the examples we just did. All right. So that's one of our applications of integration, is to find average costs. And I want to state something real quick that I sort of, a fact that I sort of used implicitly there. And something that I don't think I've really talked about in detail, but derivatives and integrals undo each other. So for instance, if you have a cost function and then you take its derivative, we should remember from this class earlier that the derivative of a cost function gives us a marginal cost function. If we take a marginal cost function and we take an integral of it, we get a cost function. We lose something in the process, though. When we take the derivative of our cost function to get a marginal cost function, it only tells us what our variable cost is, right? It tells us how much each item costs per unit, right? We lose any overhead constant costs. So derivatives annihilate constants. And that's why we need that plus c when we're doing indefinite integrals. And integrals cannot retrieve them without prior knowledge. In some sense, the problem early on in the semester where we were like this was like day one where we were talking about designing cost functions given variable costs and fixed costs, right? In some sense, if you know variable costs and fixed costs, you can construct the original function by solving a differential equation. Differential equations are an entire subject of their own. You may have heard people talk about diffie-q or that class called differential equations. There's a bunch of different ones. There's ordinary differential equations. There's partial differential equations. There are graduate level courses on it. It's a big field. One thing that I always find a little funny is physics kind of lies to students a lot as they're learning physics. Like the first time you see physics is almost definitely going to be what's called algebra-based physics, which basically takes physics and takes out all the calculus and gives you a bunch of formulas and simplifies everything a lot. And then maybe eventually you might take a physics class in college or something that's a calculus-based physics class, and then they show you a lot of the calculus and you do different derivatives and integrals in physics. And then later on, if you decide to go into physics, once again, they tell you actually all that calculus stuff we were doing, really, you were actually just solving differential equations that entire time. We just took out the differential equations part. And that's really what physics is. Physics is mostly a series of differential equations. And differential equations have a lot of really wide-ranging applications and consequences, and they are in general difficult to solve. However, there is one type of differential equation that is very possible for us to solve, and that's called a separable differential equation. So and before I go into what a separable differential equation is, first we should get a better idea of what a differential equation is. Okay? So, a differential equation I'm just going to write diffie-q from now on, is an equation that relates a function y of x to its derivative. In other words, basically the idea is that you have a function and you give it some relationship to its derivative, and then if you solve that differential equation, it tells you what functions have that relationship. So the easiest example of a differential equation, or well, the easiest non-trivial one, and the one that doesn't require any differential equation knowledge to actually solve for a lot, you can kind of just make educated guesses, is y prime is equal to y. All right. This is asking, this differential equation asks for a family of functions, or rather it asks for a function y equals f of x such that f prime of x is equal to f of x. In other words, this function, or this differential equation, the solutions to it are the set of all functions that are invariant under differentiation. Functions whose derivatives are themselves. Do we know any functions like that?
E to the x.
E to the x, yeah, e to the x is a function whose derivative is itself, and we can check that, right? If f of x equals e to the x, f prime of x is also equal to e to the x. So that one works. F of x equals e to the x is a solution to our differential equation. However, it's not the only solution. There might be other ones. For example, it turns out that if we let f of x equal 4e to the x, that still works, right? Because f prime of x is equal to 4e to the x as well. We just pull the constant out, take the derivative of e to the x, and we get e to the x back. So this is also a solution. So to solve separable, or to solve let's talk about what a separable differential equation is, and then we'll come back and we'll solve this in full generality. Okay, so a differential equation is separable if dy over dx is equal to f of x times g of y. In other words, it's separable if we can write it as two separate functions. One function of x times one function of y. In particular, we can rewrite as dy, g of y dy equals f of x dx. Then, if we integrate both sides, we get big G of y plus a constant is equal to big F of x plus a constant, where big G prime of y is equal to little g of y, and big F prime of x is equal to little f prime of x, or little f of x. Basically, these are antiderivatives, right? Then we can group our constants and solve for y. So, going back to our example, we have the example that y prime is equal to y. In this case, we can rewrite the y prime as dy over dx. Remember, those are just both notations for the same thing. Y prime is the derivative of y with respect to x. dy dx is the derivative of y with respect to x. dy dx is equal to y. And I'm even going to write y times 1 here. Okay. In this case, y is a function of y, right? And 1 is a function of x. So we can separate this differential equation, the separable differential equation, as 1 over y dy is equal to 1 dx. I'm just dividing both sides by y and multiplying both sides by dx. This is called separating the separable differential equation. With separable differential equations, once we've separated, then we integrate. So separate and integrate is sort of the mantra for solving differential equations. We're not going to see any other kind of differential equation in this class because, again, that's classes and classes and classes on their own. There are so many different ways to solve all sorts of weird differential equations. We're just going to do the easy separable ones here. So now we integrate. The integral of 1 over y dy is equal to the integral of 1 dx. I just realized that I don't have my camera on. So here I am. I'm here. What's the integral of 1 over y dy? Do you guys remember?
Is it y to the negative 1?
That is another way of writing 1 over y. But then if we try to apply the power rule to y to the negative 1, we get in trouble, right? Because we would increase the power by 1, y to the 0, and then divide by the new power, which would result in us dividing by 0, which is bad. This is the exception to the power rule. We can't use the power rule on this. What function has derivative 1 over y, 1 over blank? 1 over x, 1 over y.
ln.
Yeah, ln. So this left-hand side here is the natural log of, technically it's the absolute value of y. And on the left-hand side, we just have the integral of 1, which is just x. We do need constants. Technically, we need constants on both sides. So I'm just going to write a constant on the left-hand side. If we did have constants on both sides, ln of y plus c1 is equal to x plus c2. I could subtract c1 from both sides to get ln of y equals x plus c2 minus c1. So let c equal c2 minus c1. They're both constants, so their difference is also constant, right? In general, when doing differential equations, this is something that's going to happen. We're almost always going to just have one constant, and we're going to pull it over to the x side rather than the y side, so that it just gives us less work to deal with. And we'll talk about what to do with that constant, because there will be some cases where you have to actually deal with that constant. So we have ln of the absolute value of y is equal to x plus c. At this point, now that we've separated and integrated, all we have to do is solve for y. To get this out of the natural log, we should do e to the power of both sides. E to the ln of the absolute value of y is equal to e to the x plus c. But e to the ln of the absolute value of y is just the absolute value of y. And e to the x plus c is e to the c times e to the x. So this e to the c, that's also constant. So once again, e to the c, I'm just going to replace it with c. The absolute value of y is equal to c e to the x. Since the absolute value of y means that this is either positive or negative, what we get is that y is equal to plus or minus c e to the x. But plus or minus c is still just constant. So there's our family of functions. This is called the general solution to the differential equation. the general solution to a differential equation you can think of as the antiderivative, right? In the same way, it's the family of all the possible solutions to the differential equation. We can also find, so the general solution to a differential equation is y equals f of x, where f of x represents a family of functions that are all solutions to a given differential equation. We can also give a specific solution to a differential equation is y equals f of x, a single function with no unknown constants that satisfies some given initial condition. Sometimes problems where you are asked to find a specific solution to a differential equation, sometimes these are called initial value problems. Or IVPs. So basically, when coming into differential equations, when looking at them, I'm only ever going to give you separable differential equations that can be solved by separating variables into all the y's on one side with dy, all the x's on the other side with dx. And then I'll ask you to potentially do one of two different things. Either find a general solution to the differential equation, which is going to be some function with some unknown constant in it that you'll give as just a family of functions that answer the differential equation. Or more likely, I'm going to ask you for a specific solution to an IVP, or an initial value problem. Okay? So, for example, suppose your marginal cost to produce a t-shirt is $10, and if you produce no t-shirts, it will still cost $100. Right? What is the cost function C of x for the cost of shirts in terms of X shirts produced. So, first of all, this is not something that you actually need to use a differential equation to solve. I'm just going to show you how you could use a differential equation to solve, and then we'll do another one where you actually will need a differential equation. Okay. We know that we could just solve this by saying, all right, well, it's going to be C of X, the cost of X, is going to be the variable costs times X plus the fixed costs. So our answer should be 10x plus 100. So let's go ahead and solve using a differential equation and find the solution to the IVP and verify that we get the same answer. So we can also view this as an IVP, where the marginal cost, the derivative of the cost with respect to X, is equal to 10. And C of 0 is equal to 100. Here, this is in fact a separable differential equation. There's no C's or X's, so it's really easy to separate. dC is equal to 10 dx, and then we can integrate both sides. The integral of 1 dc is just equal to c, and the integral of 10 dx is equal to 10x plus a constant. Oh, that's annoying. This is little c here for the constant. But we can solve for our constant by using our initial value. We know that C of 0 is equal to 100. So we can plug in 100 for C and 0 for X plus little c. So 10 or 100 is equal to 10 times 0 plus c. So 100 is equal to c. And we get that our function, our cost function, C of X, is equal to 10x plus 100. As desired. So just like I was babbling on about the case in physics, secretly we've been using differential equations this entire time. They've just been differential equations that were simple enough to model that we didn't need calculus to deal with them, actually, right? If your costs are constant, then you can just model things linearly. But if your costs are different based on how much you produce, you can still use this method to solve for your marginal cost. For instance, you can take your marginal cost, your cost per unit, and retrieve a cost function. Right? So let's do one more example of a intermediate or an initial value problem. This one kind of out of context. So let's say, so solve the IVP where dy over dx is equal to y times x squared, and y of 1 is equal to 2. So initial value problems come with two parts. They come with a differential equation and a initial condition. For the word problem above, we identified our differential equation as the marginal cost. Dy over, or dc over dx was equal to 10. Here it's just flat out given to us. In the last problem, we had to take our initial condition from our fixed overhead cost. The cost to produce 0 units was $100. That's the initial condition. C of 0 is equal to 100. Here, we're just given an initial condition. And the first step for solving the IVP is, it's a separable differential equation. Let's separate and then integrate. Okay, so we're going to rewrite this. Usually the first thing I do is I rewrite it as dy is equal to y times x squared dx. I just move the dx over. And then we're going to divide both sides by y. So we get 1 over y dy is equal to x squared dx. Now for the first time, we've had actual things to integrate on both sides. It hasn't just been constant on one of the two sides, but our technique doesn't change at all. We've still separated. We've got something in terms of y times dy is equal to something in terms of x times dx. And now we need to integrate. As before, the integral of 1 over y is still ln of the absolute value of y. And the integral of x squared is x cubed over 3 plus a constant. Again, technically we do get a constant on the left-hand side. We're just collecting all the constants on the right-hand side so that we don't have a bunch of extra constants hanging out. Now we can solve for c using our initial condition. This is us recovering our fixed cost, basically, or our fixed value. We know that y of 1 is equal to 2. So that means that when y is equal to 2, x is equal to 1. So ln of 2 is equal to 1 cubed over 3 plus a constant, which means that c is equal to ln of 2 minus 1/3. So we can plug that back in and get that the natural log of y is equal to x cubed over 3 plus ln of 2 minus 1/3. Once again, to get the y out of the natural log, we should apply e to both sides. So e to the ln of y is equal to x cubed over, or sorry, e to the x cubed over 3 plus ln 2 minus 1/3. The natural log of e to the ln of y is just the absolute value of y. Sorry, e to the ln of the absolute value of y is just the absolute value of y. And over here, we can simplify this just a little bit. That's e to the x cubed over 3 times e to the ln of 2 divided by e to the 1/3. E to the ln of 2 is just 2. So the absolute value of y is equal to 2e to the x cubed over 3 divided by e to the 1/3. And then we need to decide, whether the absolute value does something or not. Y is equal to plus or minus 2e to the x cubed over 3 over e to the 1/3. Well, our initial condition helps us here too, that y of 1 is equal to 2. We know that when we plug in for x, when we plug in that 1 there, we should get 2 for y. So that means that the right-hand side needs to be positive. So this has to be plus. So y is equal to 2e to the x cubed over 3 divided by e to the 1/3. And that's our solution. All right. And I think that is going to just about do it for today. That's a fair amount of new stuff. We talked about average value, and we also talked a little bit about separable differential equations. We will work a little bit more with these separable differential equations, and we'll do some more of them in context next class. I will post an assignment for average value stuff and for separable differential equations here in a little while. And other than that, does anybody have any questions before I let you guys go? Also a reminder, quizzes were due today at the beginning of class. If you didn't get it in, I'll open up the deadline for a little bit longer just so you can get them in. Please get them in before the end of the day today. Otherwise, I'm going to start taking off points. And also the survey linear regression was due today. So I will take a look at those either tomorrow or Friday. Okay.
My group needs a little bit of help with the linear regression stuff. None
Yeah.
of us have the packet, so we weren't able to look back at it.
The packet? So I posted
yeah,
it.
Was it on D2L?
No, it was on Discord.
I didn't see it.
I'm looking right at it. It's after the U substitution practice from yesterday, but before the whiteboard post. MAT125 linear regression.pdf. If you want to show me, your data, I can take a look at it and see if I can answer any questions for you.